So it's my pleasure to introduce Hoifang Poon. Hoifang is the Senior Director of the Biomedical NLP team at Microsoft Health Futures, and he's also an affiliated professor at the University of Washington Medical School. At Microsoft, he leads Project Hanover, which has the overarching goal of structuring medical data for precision medicine, including biomedical literature, which I think is a topic that many of us here are interested in. He has given tutorials on this topic at several top conferences, and his prior work has also received Best Paper awards from premier venues like NACL, EMNLP, and UAI. Please take it away.
Thanks so much for inviting me. So good to see all of you. So good to see Doug. And I'll be basically sharing some of our work on how do we advance AI for precision health. But let me first start by motivating the topic a little bit, right? So I will introduce what does it mean for precision medicine, and also crucially why AI or NLP might actually have a role to play here, and then dive into some of the biomedical NLP work that we have been focusing on, and then conclude with some kind of future direction and also some kind of like immediately tangible progress. So I would love for this to be as interactive as possible. I do realize that we started a few minutes late, so but feel free to interrupt with any question and comments and suggestions and everything. I will probably go relatively fast, have a bunch of material to cover, but feel free to stop me anytime when you guys want to learn more, and that actually would be crowdsource the attention mechanism, right? to the deck. So let me start by, some of you might have seen the graph to the left, right? When I first saw it, it was pretty shocking. Basically, in the ideal world, you want every patient to respond to the treatment they have been prescribed to, right? Which is signified by the blue person. But unfortunately, in the real world, a lot of patients actually do not respond to the treatment they have been prescribed to, right? If you think about cancer, the standard of care actually, especially for late stage, is still quite poor, right? Often it's the minority that actually even just have a response, right? It's only the minority patient. Now, from a machine learning point of view, you can think about it as almost like a basically underfitting problem, right? Traditionally, we don't really have that much high resolution information about the patient, right? And thereby, it's very hard to distinguish the red and the blue a priori. So take cancer as an example, right? So, traditionally, the classic cancer joke is like lung cancer doctor don't talk to blood cancer doctor, right? Like they completely separate by the originated organ. You have really coarse feature like looking at the some radiology imaging, looking at the tumor size, right? Maybe if you got a biopsy, looking under the microscope to see what some of the patterns and so forth. But the good news is that with the advent of big data in medicine, things start to promise to have change for the good, right? Again, cancer genomic is the poster child of this, right? So if you recall 20 years ago at the conclusion of the Human Genome Project, it took actually tens of countries, over billions of dollars, and over a decade to sequence a couple of human genomes, right? Nowadays, actually 8 years ago, the cost for a single sequencing a human genome has dropped to $1,000 by the announcement of Illumina's X10, right? Recently, as a company just came out of stealth, announcing that they have now $100 genome, right? So, and from cancer biology, more importantly, is that we know that cancer is driven by all those genetic mutations, right? So, and so by actually having the tumor genome, we are literally staring at the source code for the cancer, right? So we have the opportunity to differentiate down to the individual level. And then there is another really kind of like maybe even more important disruption that worth highlighting, but often tend to be understated, which is the rapid digitization of medical records, right? So what does that do? It's actually had a relatively recent event, right? So it's basically starting from the high-tech act in 2009 in the US, and actually in many of the other, even the developed country, the EMR is not as universally adopted. And what does EMR give you, electronic medical give you, is this really kind of like high definition, longitudinal kind of trajectory for a patient from diagnosis to treatment to outcome. And later on, you'll see that there is actually a lot of potential information barrier inside there that could be used to actually improve clinical care and accelerate clinical research. So that led us to sort of the prospect of this whole notion about precision health, which is like, can we actually differentiate patient down to sort of like the very kind of like precisely figure out what's the disease architecture and mechanism, and then precisely target those kind of like areas so that the treatment can be much more effective, right? And you can roughly think about there are two big areas. One is obviously on the clinical care side, that's in the hospital with the, let's say, oncologies and others, right? That actually treat individual patient, right? Try to, and some of the potential, growth area is like, can you, do decision support and so forth. But also the other, on the flip side of this, is the clinical research. This is where you actually inventing new drugs, right? This is where you actually figure out whether treatment is really work or not in the practice. And obviously there is a infinite continuum between the two, right? Oftentimes you gather data from the clinical care that can inform the clinical research, and then you develop new treatment, and then you hope to put it in practice. When you look into the practical progress, there has been actually a lot of challenges, right? On the clinical care side, first and foremost, like there is even a lot of kind of like challenge in how can we actually take some of the cutting edge treatment and level the playing field so that everybody can actually have access to those, right? So in some of the developed countries, obviously well known that the resource is very kind of like poor. Even in the United States, right? So the majority of patients are actually treated in the community hospital rather than this very big so-called NCI designated cancer center, which obviously have the best expertise and information, right? Here's one true story I learned from one of my colleagues. So she has a brother who got diagnosis of leukemia actually in Spokane, right? So he went to the Spokane hospital, and then they basically give him a pretty pessimistic prognosis, like a few months, right? So my colleague persuade him to go to Fred Hutch in Seattle, right? And they actually find a trial for him, right? That matching, which actually now he's actually in remission for 2 years, right? So that can be actually pretty drastically effect. And the question is that can we actually develop technology to some extent like level the playing field? And then on the flip side of the clinical research, right, the challenge is also very daunting, right? So some of you might have already know this statistic. Like when I first heard about it, I thought it's a typo, right? So somebody tell me that an average FDA-approved drug costs $2 to $10 billion. I thought does it mean 10 million, $2 to $10 million, right? And then but when you actually understand how the drug development works, you start to understand why it's so expensive. For example, the mean number of patients in a phase 3 cancer trial, right? So many of you probably know that you go from testing on the cell culture, and then try to kill enough mice, and then you basically start to experiment on humans, right? Phase 1 to 3, and the phase 3 is really the last one before the approval. You tend to need, often the mean number of cancer trial is like 3,000. So, and then multiply that by every single patient, that costs, tens of thousands of dollars. And that easily one trial could be 100 million, right? So, and then many trials fail, right? Unfortunately. So, and then, and there is a lot of inefficiency in the whole process. We can talk more, but long story short is that there are so many challenges. There is this tantalizing prospect that we can really drastically accelerate clinical research and improve clinical trial, but so many challenges. And the hope is that to see whether actually there has been some pockets of opportunity where AI can actually help, right? So that kind of motivated a lot of what our research agenda. Obviously, I started as an NLP person, so I basically look under the lamp, right? So there has been a lot of work that focusing on how can biomedical NLP help, right? And that motivated a lot of work in exploring all kinds of self-supervision approach, because we often don't have a whole lot of label data. But then there are also some exciting frontier beyond the NLP that I will sketch at the end of the talk. But most importantly, right, obviously, we really want the end-to-end application. So we start to make some progress with some of the actual real-world engagement that give us a lot of end-to-end kind of scenario, stakeholder, and also data that we can validate the potential for the AI algorithms. So one realization, I'm sort of half joking about the NLP, but actually it turns out that it could actually play a really key role. And one of the reasons is because a lot of the healthcare is actually conducted in natural language, right? So naturally, a lot of the information actually buried inside the natural language, right? And also this obviously interact with other modality, right? Like in the hospital, people use transcription to record the medical records, right? And then you have actually one thing people interpret machine reading in the hospital is that they thought we are doing OCR, right? Because actually one of our collaborating hospital, half of the pathology report are still in scanned PDF. There is various reasons we can whine about it in the whole healthcare system. But anyway, and then from the NLP side, obviously there is a lot of generation work, right? But what we find out is that often a lot of 80-20 is actually on the natural language understanding side, specifically on the machine reading side, which is what I will be focusing on. So briefly, right, I don't need to preach machine reading. It basically literally originated from Oren and here, right? Doc and so forth. So, but briefly in the biomedical context, right? Think about, let's say you have a snippet from PubMed, right? It basically says that, hey, there is this patient cohort, there is some of this gene mutation. These guys were treated with a certain drug, and then they show partial response, right? So from this piece of text, you want to obviously extract the key entities, right, like drug, gene, mutation, but more importantly, you want to figure out that it was talking about certain relation among them, right? Like in this particular case, it would be saying that if tumor have this kind of gene mutation, then this drug might actually be helpful, right? Obviously, like the first thing, obviously, to look at is actually what you guys have been doing, right? Which is like, can we actually reduce all those unstructured, 30 million papers into, highly structured, knowledge graph or hypergraph, right? So the nodes are the entities, the edges or hyper edges are the relations, right? And so here's one actually concrete motivating example that get motivated a lot of our earlier work, which is the so-called molecular tumor board, right? Many of you probably know tumor board actually have been sitting around for a long time, right? The common cancer joke is like slash poison and burn, right? So slash is the surgery, burn is the radiation therapy, and then the poison is the traditional chemo, just kill every dividing cell, right? And that's you're just doing carpet bombing, hopefully take out the bad guys, but obviously you kill lots of civilians, right? So, and then there is a big movement in cancer treatment is to start thinking, again, in the precision medicine direction, right? We understand that actually cancer are driven by some of this individual mutation. And then what do those mutations do? I mean, biology, especially protein biology, are just Legos, right? So they have, each protein have taken different shape, and then those shape actually allow us to bind to each other and then do stuff, right? And then, so if you can figure out, here's the mutant protein that the cancer depends on, and in particular, here's the mutant domain, mutant shape that are different from your normal protein shape, right? Then there is a possibility to develop essentially a guided missile, right? Basically a small molecule to bind to those mutant domain. Then you can neutralize, the cancer, the driving protein, right? Just like how neutralizing antibody works for COVID, right? And so so that is actually the molecular bit, right? So that is like, okay, if we can now sequence the tumor genome, right? Then we have a lot of those candidate kind of mutants, right? And then farmers start to pour in billions and billions of dollars to actually develop new drug to target those things, right? So this is called a targeted therapy. And there was actually quite a bit of spectacular progress, right, exactly in the past 1 or 2 decades, right? So let me give you one data point. So 10 years ago, if you look at the genomic application, right, you feel, actually that's when I started in MSR, looking at the field, I feel a little bit depressed because there hasn't been a whole lot of very practical, tangible things, right? But just within the past, few years, there were just tons of new drugs. Right now, there are actually over 1,000 drugs either approved or in the pipeline for cancer, right? And then if you look at some of the really the top mortality cancer type like lung, right? Actually, half of those sequence mutant actually are actionable. Meaning that if you look at the average patient, right, 50% of the chances you will find some actionable mutation that there is a drug that targets them. So that basically make it mandatory that actually for some of those patients that you really should sequence them. But then what do you do with the information that becomes the big bottleneck, right? Because human genome had 20,000 genes. There were over 1 million variants that have been observed, right? There are thousands of variants we know something about it, right? And then on the other side, there were over 1,000 drugs and trials and so forth. And so how do you actually deal with those information overload? So that's actually one of the angle for NLP to help, right? So in fact, this is Memorial Sloan Kettering. They form a team. These are the team that basically their job is to read PubMed papers, right? To curate information that can support the molecular tumor board, right? This is a reasonably big team, but they can only cover a fraction of the things, right? Like think about your homework assignment for the day is 4,000 paper every day, right? For 365 days. So you got to need some help, right? So that's kind of like one of the first angle that NLP can obviously potentially help to turn them into like superhuman curators. And then more recently, there were actually we find that there were actually another big body. Oh, sorry. Yeah.
Actually, I had a question on the previous slide.
Yeah.
So can you give an example of what is it that they're
They
looking
try to
for?
curate? Yeah. So one of the example I put earlier, the drug gene mutation, that is one of the marquee information they have been trying to curate. So basically, the most immediate thing is like this guy have this tumor genome, right? And then you identify here are some of the notable mutation on potentially cancerous genes. But then what do we know what to do with them? So the the most direct thing is like, do we know, for example, does this mutation confer resistance to the drug or actually make it sensitive to the drug, right? So that drug gene mutation relation.
So as long as the assumption here is that this is worth doing because if you can populate this database with structured data, then there's other systems in place that help with like matching or like proposing candidates.
Yeah. So this is this one bit, this OncoKB is specifically for what are the actionable insight related to the gene mutation.
And this isn't something that you could ask authors to provide when
Perfect. So this is a question that one of my favorite questions I always get asked. The short answer is that there are several reasons why this hasn't taken off. So first of all, this idea actually is worth exploring because some journal like Cell Press actually are looking into this.
Okay.
But unfortunately, like there has been some like first of all, the challenge is several fold. One is like you often don't know what are all the granularity you want to put in, right? So for example, there is a reason people write a short thing for called abstract. They call out all the important findings. But if you look at a lot of this information that are worth extracting for actionable, like molecular tumor or what have you, they actually lie in the full text. So the abstract just don't have enough real estate to capture those. And often the author may not actually know that certain piece of finding later on become really important in solving some other puzzle, right? And also there is a comparable movement that people have been in semantic web. Actually, people try to do the same thing, right? Let's force the HTML writer author to structure it so that we can. But if you talk to semantic web people, they retreat it, right? So because it's just infeasible for the author to anticipate what are all the detailed granularity information people want, and then come, and sometimes even the ontology keep expanding, right? So you may not actually know that this piece of information later will be tied to something, a new concept and so forth. So short answer is that people have tried, hasn't taken off, but what we suspect is that maybe in a sort of assisted curation fashion, we can revive, actually make it this works. So the whole idea is like, authors certainly have incentive structure to make things more searchable, right? But if it takes too much work, right, they have too many grants to write or too many papers to compose. So, but if you make it super easy, and then maybe they will do it. But also, you can also imagine, if you already do 99% of work, you can even have reader in a Wikipedia fashion to even validate them too, right? So, any other questions?
I was just going to say, my supervisor, Gary Bader, works on exactly that problem. So he leads the biofactoid project.
Mm-hmm.
I'm not sure, you said cell press, that is actually who he's like working with.
It could be him, yeah.
Yeah, so yeah, you can check out biofactoid. It's
I'd love to if you.
Yeah, I don't want to take too much time, but it looks like that, and the author is supposed to go in and curate and say these are the genes, this is the pathway.
Yeah.
It's like exactly what you're talking about, and he's also to your point about like incentives and stuff. He's talking to economists, trying to figure out what's the incentive for biologists to do this. Highly relevant and very interesting.
Yeah. There are several pieces of information where structuring is complete success, right? Like, for example, protein database, right? You don't need to try to parse text to try to figure out what's the protein structure, right? Like every protein, people structure them and in a certain language and then put them in the PDB, right? That's how we actually get AlphaFold training data, right? Another example I learned is something called phosphorylation. That's a very special kind of enzyme action. There is a database where actually people can actually put the structure information in. So when you have a very sort of like narrow, well-defined but also high value piece of information, that's doable. What's really hard is to anticipate every single other things, right, that might become relevant later on. But the hope is that NLP could help, right? So like it's fundamentally just like you have a giant haystack and you try to look for some needles, right? And the human doesn't have the skill to navigate the haystack, but the NLP, even relatively crappy one, can filter out a lot of the haystack doesn't look remotely like the needle, right? And now you present the needle candidate, and then the human expert, like it's like a lot of problem is NP hard, right? Like which means the verification is easy, so human can very easily verify them, right? So anyway, so any other question before we move on? So so obviously we start with the literature, and again, you guys did fantastic work there, right? And then in recent years, in recent 5 or 6 years, we start to also focusing on electronic medical record. And the first revelation is that this is another giant body of biomedical text, right? So for example, you take a cancer patient, right? He or she may have hundreds of notes, right? From encounter notes, pathology report, radiology reports, and blah blah blah, right? So, and then those notes actually contain a lot of high value information about, again, the patient trajectory, and then if we can unlock this, right, then we can potentially facilitate this very exciting area called real world evidence, right? So first of all, let me explain what does it mean, right? when you hear, you may start to see the term like real world data, real world evidence. And initially, like when I first saw it, right, it seemed nonsensical, right? Like, does it compare to fictional data or something like that? and turns out that what's trying to contrast against is actually clinical trial, right? So in a clinical trial, you have a carefully crafted, like here is my intended patient population. Usually they try to put it as narrow as possible to ensure the like maximize the success probability. And then here's the hypothesis I'm looking at, right? Here's the primary endpoint, secondary endpoint. Here's the intervention, right? Case controls and so forth, right? And also you carefully plan out that not only that, but you also use this kind of like, ultimate weapon of modern scientific medicine, which is the randomization, right? So you use that to, eliminate the confounders and all that. Now, real world data, by contrast, is something that you observe in the wild, right? So here are patients going to a hospital and then they get treated, and here are all the data points, right? So compared to clinical trial, you have no control about their generation, right? So you have to be aware of lots of potential confounders because these are fundamentally observational data, right? But if you can deal with some of those challenges, then this is a giant pool of free lunch, right? So every single day in the hospital, somebody is doing tons of experiment. And if you can collect those data points and then unleash the information inside it, then maybe you can make a dent on some of those billions in the clinical trial process, right? So again, we already covered this, but this is both a depressing and exciting graph, right? Which is depressing because it's so hard to get a new drug. And also when you think about in a precision medicine era, this is even harder because you're supposed to, develop more drug, right? To deal with more smaller and smaller subpopulation, right? So if yesterday's model, if this model already going to bankruptcy yesterday, then tomorrow it will be even worse, right? But the one of the promise is for real world evidence is that if we can leverage all those free lunch, we can actually impact a lots of these processes, right? And particular in the clinical trial and the post-market area. So let me quickly give you some concrete ideas, right? So for example, we talk about some of those early days cancer treatment, right? They are often very effective. And then there is the targeted treatment movement, right? That really generates so much excitement, and there are some miracle, cases. But when you think about it, right, one of the secret weapons for cancer is natural selection, and actually evolving kind of like resistant subclone, right? It can maybe either already have a resistant subclone within the original tumor, or maybe during the time when you are trying to eradicate the tumor cell, right? It takes time, and then some of the new mutation emerge. And so for targeted treatment, the advantage is like you actually induce very little side effect, right? Because you precisely target the mutant. But on the other hand, that also means cancer can easily, come up with a mutation. That's like, think about Omicron, right? That's a real world example. So one of the really powerful tools, turns out, is our immune system. This is what many people think would be the cancer end game, right? So in the end, we have to mobilize the immune system to deal with it because the immune system has a built-in natural selection mechanism, which I would not go into detail. That's a fascinating topic that I personally am very excited, but it would take hours to explain. But long story short, there are this one mechanism that cancer leverage, which is that your immune system has a brake system, right? So your immune system also can be lethal if your immune system just start launching attack, right? That's called autoimmune overdrive. That's actually how COVID severe patients' lung get collapsed, right? Which is basically they get my immune system freak out, just attack and then kill a lot of the normal cell. So there is a brake system to kind of temper the immune system, and cancer basically evolved to leverage this by sending a signal, right, to the immune system to say, okay, sleep, right, shut down, right? So then the immunotherapy, one class of very successful immunotherapy, if you look at the Keytruda, right, it's really a wonder drug. And what it does is to by cut off this signaling pathway, right? So anyway, long story short, this is very exciting. It worked miracle for some of the really late stage one, but it only sort of like actually get response for minority of patients, right? For majority of patients, they either don't respond or they have autoimmune overdrive. And so then you want to ask the question, how can we improve this, right? So one potential way is like, if we can actually tally the real world data, find the exceptional responder, find the non-responder, then we may be able to compare what are they different, and then may be able to actually figure out something out. But even some simple thing like, okay, did this guy respond or not, right? Even that simple piece of information usually are not in structure form. So then you actually need NLP to extract, right? And then another quick example, we talk about how much the clinical trial is expensive. Now, it turns out that the control arm is actually measuring usually the standard of care, which by definition actually have already been practiced. So people actually show that if by collecting the information from the EMR, you can actually do away, well, maybe not the whole control arm, but actually at least recruit many fewer patients, right? And there is this company that really a pioneer, trailblazer, except that they have to hire over 1,000. And these are not your Turkers, right? These are the highly specialized folk who can understand EMR, understand all the medical ontology, and can curate this thing. And they can only still curate a fraction of the patient, right? So, like in the US alone, there are 2 million new cancer patients. One cancer patient just curating basic information take 2-3 hours, right? So you can do the math and see what's an army you have to recruit. So then the flip side of the question is that can we empower all these folks? So I realize I'm running a bit out of time, so I will skip some of this other case, but I mean, clinical trial matching, we've mentioned that, right? That's really important, and lots of text actually specifying what the trial. So if you can parse the EMR, you can parse the trial, then you can easily do the matching. And also after the drug get approved, you are not done yet, right? There are so many things you can actually do, and a lot of costs, and right now it's not efficient at all, that you can have impact. So that's a little bit of long-winded introduction to hopefully convince you that there is some good we can do with NLP here, right? So any quick question before we move on? So I will go very quickly because you guys, I mean, very familiar. So one challenge is the variation, right? That there are so many possible ways you can say roughly the same thing, right? On the flip side of it, there are the ambiguity, right? So the first thing I figure out that there is something interesting going on in the PubMed is that there is this gene that really pop up everywhere, right? Which is called PDF, right? And turns out that there is actually a gene really called PDF, except that most of those mentioned in the PubMed doesn't mean the gene, right? So then you need to resolve it. And then also, so those two are obviously the bread and butter for any NLP domain. But in the biomed, actually, there is also one big distinction, right, from the general domain, from the newswire, from the web, right? So in the newswire and the web, oftentimes the high-value information you care about often have lots of redundancy, right? So that you may not need to tackle the hardest linguistic phenomenon cases. I mean, Doug and Lauren know all this too well, right, to leverage that. But in biomed, oftentimes the highest value information have exactly the little or even zero redundancy. Right. For example, a paper just find out something in last week's New England Journal of Medicine. This could be a life and death information, but it's only in this paper, right? So and then if information like, okay, in this case, like to extract this relation, you have to cross paragraph, right? You really have to really bite the bullet and get the information out. You really have to leave no facts behind, right? Basically, and then. And sometimes, like for in the EMR real-world evidence case, sometimes you even have to cross documents, right, to even determine something similarly simple, right? Here's a patient. What's the tumor type? What's the histology subtype, right? Even some of this information, actually, you have to compose multiple pieces from different reports, and then you can figure out the actual types, right? Now all of this, eventually, we have this big gun of machine learning, right? But here is also what in biomedicine, we sort of lost some of the potency of this big gun because and it's very hard to crowdsource, right? So it's much harder to crowdsource. Imagining you asking your attacker to interpret this genetic paper or read that CT scan for you, that would be much harder, right? So then we need to figure out alternative way. So one possible potential is actually trying to figure out a lot of other free lunch. So I assume most of people see the cake, right? So so the whole idea about self-supervised learning, right, is that you want to leverage, a lot of this kind of free lunch. Now, a lot of focus has been on pretraining. Obviously, I don't need to belabor you guys on, but what I want to point out is that this is just mostly focusing on the text, unlabeled text style, right? So the language model pretraining often is very knowledge poor, right? It's very ignorant about the world. So what we have hoped to actually explore a lot, and again, many of you actually did a similar thing, which is like there is also a lot of domain knowledge, especially in all these high value verticals, right? So there are complete, for example, there are complete ontology about human genes, right? All 20,000 genes, you can look up. That's how I look up the PDF, right? And so how can you leverage that, right? So if we can leverage both the knowledge and then turn it essentially as a hallucination engine to create lots of noisy label data, that we may be able to bootstrap the NLP and machine reader, right? So that's really the whole scheme. And one thing that we tend to think about it is like we only have those domain experts for so much cycle, right? We cannot expect that we can get millions and millions of label data from those domain experts, right? What's the best way we can utilizing their bandwidth and so forth, and how do we find a free lunch, right? And then eat it, right? How do we leverage the knowledge? And then the last one is about sort of like in domain specific training. So let me start with that. But so I will go really fast here, but feel free to stop me. All right. So I don't need to tell you why how language model works, right? I just want to point out that a couple years ago, when I start thinking about this domain, right, we find that actually there is a fierce arm race in the general domain, right? But actually, biomed is obviously somewhat an afterthought, right? So, and everybody assumed that, okay, here we have a general domain BER, why not we kind of build on top of that, right? So, and the common assumption is like, more data usually help, right? So, but when you think about it under the hood, actually that assumption may be actually a little bit questionable, right? So more data tend to help. You basically are thinking about transfer learning. And transfer learning, you have a source domain, you have a target domain, right? So the classic scenario would be like if your source domain have tons of data, your target domain have very little data, right? Then that would be how things will work. But let me first come here. But when you look at PubMed, right, it's actually really not the case, right? So PubMed abstract alone, you have more data than the Wikipedia plus books, right? When you add the full text, right, you have an order of magnitude more. So, and then also another thing that we have noticed is that, when you look at the vocabulary, right, that's basically how you deal with the outcome. Vocabulary word is you generate. I mean, you guys know how this, right? But the real point about like things like WordPeace, right, BPE, is that they are corpus dependent, right? In some sense, they are kind of like Hoffman code. You look at the frequent subword, right? You try to compile them. And not surprisingly, if you start from general domain, right, then you actually diluted your vocabulary because you're emphasizing the frequent word in the general domain, not the important word in the biomedical domain, right? So the first thing actually leads us to the PubMed BER work is actually when we look at some of this relatively common biomedical term, and we saw that they basically get shattered into this completely meaningless subword. So then we feel, okay, this is wrong, right? And then when we combine with the insight about this, then that really leads us to portraying the PubMed BER work, right? I should point out that you guys, the cyber actually are doing essentially the same thing. right? Except that you combine biomedical and CS. So we are trying to go all the way to biomed, right? And then, so there are some, promising. One thing I want to highlight is that, I mean, a couple of years ago, everybody, I mean, like you guys, right? Everybody's trying to scramble, try to do something meaningful for COVID. So we did a little bit of that. One of the really interesting findings is that even with like the base model, right, in this COVID specific scenario, we actually beat, some of the really big models, right? And there are some other models that I would not name here, but actually we find that we try very hard to make them work internally, but we find out if you have this very specific application domain, and then actually the domain specific model actually outperform them. So in general, I would say that does that mean that we don't need big model? Absolutely not, right? So if you have a scenario where you really don't have any idea what's the next thing come, where is it, right? Like if you have a web search or open domain QA, right? You really don't know what's the next query come from. In that case, of course, you want to memorize as much as possible, want to have as big a brain as possible. But if you only have some application area you care about, then that's when the equations start to change, right? And I think it would be very interesting to see, like, for example, with all the prompt engineerings and all that, right? To see where is the boundary lies, right? I suspect like you can't really do everything with GPT-3 or whatever, Flamingo or whatever, right? With just prompt engineering, and for a specific domain application. But there is a question: how much you can push them to, and how much actually really you have to use the domain-specific model shine. I think that would be a very exciting area to explore. Now, one thing we also did a little bit of research is on what if you have a high-value domain, but you have a subdomain within it, right? So you have this biomed domain, but when you think about it, PubMed actually really just representing a literature, right? So the medical node actually look very, very different from the PubMed, right? Now they are still infinitely closer compared to Wikipedia plus books. So PubMed, that's why PubMed first still actually tend to work. But here is actually we start to find some really interesting transfer learning trade-off. I can probably talk more about the detail offline, but the high level gist is that, let's say if you only care about oncology, right, about oncology nodes and others, right, and if you have enough oncology nodes, in this case we do, right, then actually pretraining from scratch again actually outperform even the PubMed for oncology applications, right? So, but if you don't have enough oncology nodes at like when we started at the beginning, actually the PubMed still actually work reasonably well. So, so that's some kind of like so I would probably go really fast. I mean, everybody here knows the distance supervision. I would really just skip all this, but you guys also definitely familiar with data programming. I just want to mention just very quickly, one unifying framework we try to come up with is like, so, I mean, you have distance supervision, which is great, very scalable using the knowledge base to hallucination data, but it could be very noisy, right? You could have data programming, which you ask the domain expert, right? Like you provide them with a lunch and then help them to come up with a few rules for you. But oftentimes it may be precision, high precision, but then lacking the recall, right? And then the rule may be contradictory with each other, right? And also sometimes maybe you can leverage some phenomenon to do joint inference, like coreference and some other things, right? Now, the gist of all this is that they are all noisy, and they can be very contradictory with each other. But as long as each of them have some signal, then you want to leverage them, right? And so one thing that we have tried is actually try to come up with a unifying framework based on graphical model to combine them, right? So, for example, you can think about each of these. Z is a latent variable, latent label that you wish you know, right? And then if you have some of from the knowledge to define those factors, then you can actually define a graphical model. And now at the beginning, you really know nothing about those labels, right? So that's just uniform distribution. But once you actually have inject some of the domain knowledge or linguistic knowledge and so forth, then you can start to actually reason about their distribution. And what you can do is that you can basically, I'll skip some of this, you can basically turn this into essentially using the probabilistic reasoning to compute the marginal of those latent labels and then treat them as probabilistic labels, right? And so in this way, the more knowledge you can incorporate, then the distribution will be further away from the uniform no information case, right? And so in some sense, the knowledge is basically the prior you try to inject, right? And then in that case, once you have those probabilistic labels, you can just train your usual deep learning network, right? And then after this work, we have then tried to extend it to say, okay, in the deep probabilistic logic, we still need to define those factor by hand, right? So we still need to pre-specify them from the prior knowledge. But you could actually potentially incorporate like structural learning to actually come up with new factors. You can also do it in an active learning fashion, except that you are not asking for label for one instance, but you're asking the expert to check actually the whole probabilistic rule, right? Whether the probabilistic rule matters. So again, apology, like because of the time, I can't go into some of the detail, but there is some early promising result in some of the very simple domains. So I maybe want to just quickly talk about this CRISPR work. You can guess why we come up with this acronym, right? So, but fundamentally, we care about entity linking, which you guys are familiar with, right? So you saw the MS here, right? You try to see, okay, what does this mean, right? So there actually could be many possible concepts, right? And so that's the ambiguity part, right? So of course, there are the variation, right? There are many ways to spell like multiple sclerosis, for example. There are the ambiguity, but also, most importantly, there are the giant vocabulary. So UMLS have 4 million concepts, right? So the largest entity linking data set have 30,000 concepts, right? So that's a fraction of what you have to tackle. So how can we deal with all this? And also, I mean, related to the conversation earlier about ontology keep evolving, right? You may have new concept come up tomorrow. How do you deal with that? So long story short, we basically leverage the contrastive learning and then using basically the minimal self-supervision, which are just the entity lists, right? So arguably, when you do entity linking, that's a minimal you need, right? Is at least give me the target, right? You try to link to, right? So with just the canonical name, right? And then we basically essentially just using string matching to generate the distance supervision instance. But unlike previous work that in which we try to do classification, in here we've just fundamentally just try to learn kind of like embedding, right, of mentioned context, right? So think about each entity instance, right? Mentioned instance. That is an instant embedded in the context, and you want to embed the context, and then you want to basically push together supposedly same concept, the context together, and then you want to separate the context from different one away, right? Now, once you learn all this metric, basically, right? Not necessarily canonical metric, but once you learn the embedding, you can at inference time you can just basically just do KNN, right? And this way you can actually obviously seamlessly expand to a new concept, because if you have a new concept, you can just generate new prototype. You don't even need to change the model, right? And also during the contrastive learning, you're essentially learning the synonymous expression in the context. And then you can imagine now you can using those things to warm start your next learning for like relation extraction, your QA, your retrieval, right? You can. So one thing we find most exciting about is not just that on entity linking, right? Without any label data, we can actually learn very good performance. I will skip this, but unfortunately, there are some entity linking work that are completely wrong. They completely ignore the ambiguity, and then kid themselves into saying, okay, I got very high score, so I can talk about more detail, but there is very detailed analysis about all those things. But what I find particularly exciting is that we can potentially imagine this framework to apply to all the possible semantic tasks, not just entity linking. So now we actually internally we have some promising progress in using this for NER, using this for RE, and also you can imagine actually the multitask learning is actually very natural, right, in all this. So that's a really fast apology again about the pace. But one thing I want to point out from end-to-end application point of view is that we don't anticipate replacing anybody, right? We actually want to empower the human expert. And again, I talk about this haystack versus needles, right? Analogy, and we basically want to have a self-supervised machine reader, even though they are crappy, they may be able to filter out lots of haystack that are irrelevant. And now the human expert can easily validate them. So this is actually a real UI that we have built that have scanned all those. You asked about what kind of knowledge they care about, right? The drug gene mutation. So we basically scan all the PubMed plus the PMC, and then we show each candidate finding in such a format that they can easily see the provenance. And then they often just spend a couple minutes. They can verify whether this is what they want. And so in this way that they actually become quite excited. At Jackson Lab, for example, they have a whole team, kind of like the OncoKB, not as big, but they try to curate this. And they actually have a product sell to many farmers. So they start to actually find some use here. And then for the EMR side, we also start to make some traction. And actually, for example, this is actually a prototype UI that have been used in the hospital right now daily. And of course, all this data are synthetic, right? So there is no PHI here. But one thing that I find actually rather promising is that some of those oncologists send us email actually late in the evening saying there is a forestry error for your UI. And on one hand, of course, this is not a product yet, right? So a bunch of our researchers scramble to try to fix it. Turns out it's some Azure problem. And then, but it's good to see that actually those guys start to actually take dependency on this. Well, semi-dependency on it. This one I want to quickly go over. So this is basically a graph that tally like these are the months since the treatment, right? So imagine you have a cancer patient at time 0. That's when the treatment start, right? So these are the time starting on the cancer treatment, and then on the y-axis, basically saying is like, did the cancer remain in check, right? So that's a term called progression-free. So that means like the cancer didn't grow bigger or metastasize, right? So obviously you want the cancer to stay in progression-free as much as possible, right? And this is telling exactly the immunotherapy, right? The response. And one thing that currently, literally, why the immunotherapy it's so hard to tell which one work, which one not work, right? Talk about underfitting. This is the one feature people use to determine. This is called tumor mutation burden, right? You basically count how many mutations per megabyte in average, and then using that to say, okay, this patient have higher TMB, go to immunotherapy, low TMB, go to maybe not, right? So this is basically a real-world study by Dana-Farber folks to try to say, okay, if I have TMB, right, like separate the people, what's their progression-free response, right? So you can see the yellow line are the high TMB one, the blue line are the low one, right? So this is exactly what you expect to see. And you see them diverge around 3 months, right, 90 days. So that's exactly what you expect to see. So this is actually a kind of like, not like groundbreaking thing, but what they're trying to show is that from the RWE, you can generate actually a cool insight. The only catch is that they annotated 60,000 nodes, right? Trying to build an NLP system to do this, right? In our case, we basically piggyback on the OncoBur, and then we use about 30 rules, right? And then based on the deep probabilistic logic, and we pretty much replicate actually a very similar graph on the providence data. So again, the point is not that this is a groundbreaking finding, but the point is that if we do have advanced self-supervised NLP method, we could probably get around very quickly to get some of this other re-study, facilitate some of the other re-study. Let me just very quickly talk about this exciting frontier beyond NLP, right? So the first thing to notice, I'll skip this, but basically want to point out that people actually have been doing RWE for decades, but they're using clean codes, right? So they're using all those available structured information, actually mostly for building, right, in the US, right? The challenge is that they often miss granularity and details, right? And they are also very noisy. Just give you one example, right? Like cancer relapse, you would think that should be something that's consistently be structured. It's not, right? One of our first project with Fred Hutch is actually trying to extract that from notes because it was not consistently documented in the ICD code, right? And so you can think about NLP is sort of like second generation RWE, where we try to unlock the information from the nodes, right? But there is also other information-rich modality like imaging, right? And also, so here there is actually a really exciting kind of like frontier, like vision language processing. Of course, in the general domain, you guys all see the DALIs and all that, right? But there is actually a lot of unique challenges in the biomed domain. Let me give you just one example, right? Your normal image net, right? Your mean size is like 400 by 300 pixel, right? In some of this so-called digital pathology domain, you have a biopsy, you cut it in thin slice, you scan them, right, under the microscope. And here's one analogy that people tell me about. If you print it in the usual printer resolution, it will be as big as a tennis court, right? So you often have 100,000 times 100,000 pixels, right? So that's single thing alone, right? Like the biggest thing that people have tried in this lens is like about 6,000 times 5,000 pixels. So there is a giant opportunity here. We did some baby step work. I wouldn't go into it. And then also like you don't just have imaging. You also have like for cancer you have omics. Eventually for other chronic disease you may have like your phone, right, IoTs and all that. So can you do multi-modal RWE? And then so this is one of our kind of like really excited potential is like can you predict like whether Keytruda work much better than the current companion diagnosis, right? But also we talk about like all these are observational data. So the next one you need to bring in is the causal reasoning, right? So you can't really trust the standard distribution. Let me just give you one simple example, right? Let's say in the real world data, you collate like these are all the guys who take Keytruda. These are all the guys who take some of the traditional chemo, right? Now when you look under the hood, you find that actually everybody take Keytruda are the really sickest patient, the really late stage, right? And then people who took the traditional chemo are the people who tend to be more healthier and so forth. Now, in that case, of course, you can't just draw conclusion based on the statistic, right? Because you may wrongfully say, okay, Keytruda really sucks because, right, the survival statistic is horrible, right? But actually, you need to actually account for the fact that actually those distributions are not random, right? So that's one area. I will skip the privacy preserving. Of course, you need to operate all under the privacy and compliance constraint. The question is that how can you make the AI effective? And then there is some, related to business models and other that I will not talk about. So these are the guys who really do the work, right? I'm just presenting PowerPoints. And then here are also all the wonderful collaborators we have worked with over the years, without whom we can't do any of this. So apologies that I realized that I go way over time. So sorry about that.